All right, hello. We are beginning a new unit going to focus on vectors. And we're going to start with vectors in the plane. And when we talk about sort of these vectors, we're really kind of looking at force and velocity, which again kind of is related to physics, but it can have magnitude and direction. So again, we're going to talk about what those mean, but magnitude is kind of how strong it is, and direction is obviously what direction it's going. So we use these directional line segments, which we basically, again, that's what I'm describing. These are vectors. So again, a line segment is moving in a certain direction. So like this example right here, okay, PQ, notice the symbol, it's like half an arrow. So it's a straight line with half of an arrow pointing up. And it's got an initial point and a terminal point. So again, that just means start and finish. And I'm going to start at point P, and I'm going to end at point Q. And again, I'm moving in this direction here. So when I'm looking at the magnitude, which again is like trying to find the length, how long is this vector? We can use the distance formula, which, just as a reminder, our distance formula is d equals the square root of x2 minus x1 squared. And then we add y2 minus y1 squared. And all of these, so again, if I start at P and go to Q, all of these lines over here, figure 6.16, that would be equivalent vectors. Those are going to be the exact same distance, the exact same direction, the same magnitude and direction. So that's why those would be called equivalent vectors. And this is sort of the terminology or the symbol we use. Vector equals PQ. And again, that little half arrow on top. So let's look at an example. Let U be represented by the directed line segment. So again, I'm given P coordinates, I'm given Q coordinates. That's for U. And then we also got to look at V, which again goes from R to S. So when we're looking at this, we're going to say, all right, to determine the magnitude, to determine the direction, I got to find the distance and I got to find the slope. So the first one I'm going to start with is U. And again, we use two lines like this to show the magnitude. Again, I'm using the distance. So I'm going to label, I like to do, which again, it really doesn't matter as long as you're consistent, x1, x2. Oops, that's not consistent, Mr. Larson. x1, y1, x2, y2. And I'm going to say distance. So x2 minus x1, 3 minus 0 squared, plus y2 minus y1 squared. And that's going to give me the square root of 3 squared plus 2 squared, 9 plus 4. So I get the square root of 13. All right, that's a good start. That's step 1 of 2. And the other option, again, is to look for the slope. So again, the slope in this case, because there's lots of ways to calculate slope. It's basically your change in y over your change in x, x2 minus x1. It's actually pretty easy because one of my points is 0, 0. So it's really just like saying 2 minus 0 over 3 minus 0. So my slope is 2/3 for you. 2/3 would be moving up and to the right, if we think about that as a slope. Now let's find the magnitude of S. So again, I'm going to say, all right, what is my x2, x1, all right, x2, x1, y1, y2, oops, x2, y2. Wow, I'm having trouble doing that. Okay. Anyways, once I get my equation set up, I'm going to have 4 minus 1 squared plus 4 minus 2 squared. And when we go through and simplify that, we get 3 squared plus 2 squared. Something in your head should be going ding, 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 because that's exactly what we had before. So one of the two. So again, so far, we've shown half. We've shown the magnitude is the same. Now when we look at the slope, again, what is my slope? I'm going to say 2 minus 4 over 1 minus 4, negative 2 over negative 3. That cancels out, and we get the same slope. So those are the 2 steps needed to show that these vectors show that u equals v. The vectors are the same. So looking at the standard position, again, if it starts at 0, 0, if its original initial point is 0, 0, we call that standard position. And if it is in standard position, then we write it in what's called the component form. And really all we're looking for is the ending. So because we know it starts at 0, 0, I want to know, where does that line end? What direction, what's the magnitude, how far is it going, but where does it end? And we do that in this form. So again, I would take my x coordinate of the vector and I would use, it's not a parenthesis, it's more of like an angle. I would use that symbol and again, put v1 and v2 right there. So this is called component form, and we use this symbol in this form, again, v1, v2. It's the endpoints of your vector. And if it doesn't start at standard position, which again, is fine, that's okay, but it has an initial point, P, and a terminal point, Q, well, then we just go ahead and we subtract Q1 from P1, and we subtract Q2 from P2 to, again, get it in that component form, where we have V1 and V2 for our vector. So again, basically, I take my starting point and I take my end point and I subtract it from my starting point, and that's how I can still write it in component form, even if it is not in standard position. Find the component form and magnitude of vector v that has an initial point, 4, -7, and terminal point, -1, 5. So again, this one does not start at 0, 0. That's okay, because we have what we need. So using this above, I'm going to say, all right, taking my vectors, I'm going to take -1 and subtract 4. And then I'm going to take, because I started with -1, I also got to start with 5 minus -7. So again, just simplifying that, I'm going to get -5 for my first coordinate here and 12 for my second one. Now, to find the magnitude, again, that's what this symbol means, is we have to use the distance formula. So again, just plugging in what I know. Now I have an x2, a y2, x1, y1, but I've already done that subtraction. We can see right here, we've already done that. So I'm just going to take my component form and I can plug it right in. So again, I had a -5 in my component form, square that. I had a 12 in my component form. I'm going to square that. And then when I go ahead and simplify, that gives me 25 plus 144, which equals a nice number, and we are able to get a nice whole answer. We always like when that happens. So it has a magnitude of 13. Couple more examples. 2 vectors, u1 and u2, and v1 and v2 are equal if, this means if and only if, u1 equals v1 and u2 equals v2. This is not a typo, okay? This means if and only if. So any other examples, anything else you get, it's not going to work. Show that u equals v, all right? So I'm going to take, again, looking at just from u, I have an initial, because it says from, and then my terminal or my endpoint right here. So as I'm going through, I'm going to determine first what my vector form or my component form is for you. And I'm going to say, all right, well, that's going to be 3 minus 0, 2 minus 0. Again, whenever it's in standard position, that is pretty useful. Makes our lives a little bit easier. And then if we look at V, again, kind of similar. I'm going to do 4 minus 1 and 4 minus 2. So that's going to give me a 3, 2 for my 2. And because, again, this equals this, we can prove that U equals V. Now we've got something, again, you've probably heard it before, scalar multiplication. That just means, again, multiplying by the same scale. And we can multiply our vectors. So again, notice that in my original vector V, I'm starting here and I'm traveling this direction. If I multiply that by a factor of 1/2, notice how my vector gets smaller. Okay, this is half the size of what I started with. Versus, keep that same type of thinking, if I multiply it by 2, my vector is going to be twice as big as what I started with. Negative V, okay, notice now, because it's the same size, but the direction that I'm traveling is the complete opposite direction. Basically my initial and my terminal points flip-flopped. And if we take look at an example of negative 3 over 2V. So again, switching my direction from what I started with and then making it a little bit longer, half. So I'm taking half of it and I'm adding it to the end of my my vector. So it's 3 over 2 is the scale. And again, you could do that where if it looks something like this, again, I've got that scalar multiplier on the outside, no problem. Use your distributive property and you can multiply it through to each. Again, vectors, these are like these geometric shapes. That's really what they are. They're have a beginning point and an end point. So what I do if I add them up is that I have to take where one starts. So start at U, go to the end point. And then when I get V, I then have to take V, which I guess it's not quite drawn here, but V looks something like this. Okay, then I would start from where I ended and then travel over this way. So this is how I get U plus V, is by adding this vector, and then where this vector ended, I then started with this vector. And again, it's kind of similar where if you get it in component form, again, as long as you match up the first terms in each and the second terms in each, you're going to be fine. This is kind of similar. Again, we've hinted at it over here where we have subtraction. So in this case, for when I do it graphically with subtraction, okay, so I start with U and then I have V. I'm still going to start with U, but then I'm going to subtract V. Okay, I'm subtracting V, which means I start at the same point and then travel from there. And then what's created in between is my answer, my vector. So you can see, hey, it's significantly different when we did U plus V. And I had to go from where I started to where I ended versus U minus V. I started at the same place and then I connected the difference. And again, that word difference should hint at subtraction. So again, if you get it in component form, just make sure you are dealing with negatives, that you make sure that gets distributed. Okay, and again, always, always, always match up ones with ones, twos with twos. The negative of v is negative v. So again, this is like the scalar multiplier before. If you get something like this, that negative gets multiplied, gets distributed to both terms. We have to remember that it gets distributed to both terms. So let's do a couple different examples. Last three examples here. I'm looking at, okay, taking v and multiplying it by a scalar of 2. So again, as I look through, that means I multiply in here. I'm going to get negative 4, 10. W minus v, I'm thinking, okay, I got to make sure that my order is important. So as I set it up, I'm like W minus V. And then I got to take, all right, so I'm going to take, again, matching up the two items that go together, 3 and negative 2. I'm going to say 3 minus negative 2 and 4 minus 5. So that gives me 5 and negative 1. And our last one, we're doing addition and multiplication, no problem. 2w, again, 2w simplified is 6, 8. So then, once I've simplified there, I need to add vector v, and I'm going to do that. Again, the order of addition, it's okay to put them in a different order. And I should get 413 for my answer.